Please welcome to the stage Dr. David Sloan, Chief Scientific Officer at Foundational Questions Institute.
Quantum theory has revolutionized science. We can see its impact on technology from the silicon transistors inside your smartphones, all the way through to positron emission tomography, PET scanners, that can pinpoint cancerous tumors for excision. It's changed the way we see the world. Classical dichotomies, did the particle go through the path on the left or on the right, have been replaced by superpositions and probabilities. The binary of true and false gives way to a spectrum between the two. Quantum mechanics is our best model of reality. It's been the inspiration for new ideas of mind and consciousness. It's the reason that we are all at this fantastic gathering today. And for all this, the United Nations has declared 2025 the International Year of Quantum. But what I want to talk about is what comes next. Now, I can't tell you what the next theory is going to be. But what I can tell you is how I think we're going to get there. There are lessons that we've learned from the past which inform us on our journey to find a deeper theory. We know that there must be some deeper theory. The reason for this is our theory of the very, very small, quantum mechanics itself, and the very, very large, general relativity, don't play well together. They contradict one another. We have trouble combining them. Therefore, there must be some deeper theory. This is a fantastic thing, because every time we have found a deeper theory of physics, a deeper theory of reality, we've reaped technological benefits, from mechanical advantage to steam engines through to electronics. We've also learnt more about the world in which we live. We've learnt that the tides are caused by the gravitational pull of the moon. We've learnt that the Earth and the sun are dynamical systems. We've learnt more about ourselves. We are formed out of atoms that were first forged in the dying embers of a star that went supernova. We've learnt that our muscles act as levers. We have learnt that electrical impulses are conducted by nerves to tell our bodies how to move. So we have gained insight, we have gained inspiration, we have gained wonder. We have seen deeper beauties and symmetries emerge every time we have searched for a deeper theory. So, if you want to come up with this new theory, how do you do it? Well, the first thing to know is that science advances through informed irreverence. Before you come up with a new theory, you have to understand the current paradigm very well. You have to know not just what the theory is, not just how to use it, but how it's built, where it came from, what its rules are, what its foundations are, what is the evidence that supports this theory. And then you have to ask yourself, are there places where I can break some of the rules? Can I change something about the theory and yet retain all the results that it has? We know in the past that we've gained insight on where we should look for places to break the rules. When the electromagnetic theory of Maxwell stood in contrast to the theories of Newton and Galileo, we knew that somewhere close to the speed of light, something had to give. Out of this, relativity was born. Now we know that at very, very high energies or high curvatures, quantum mechanics and relativity are going to have to come together somewhere. So somewhere deep in the heart of a black hole, or close to the beginning of time itself at the Big Bang, we have to have a new theory. So, when you're designing your new theory, what you need to know is that the gold standard of proof is to make a testable prediction, and then have this prediction verified by an experiment, by an observation. The Laser Interferometry Gravitational Wave Observatory, LIGO, was built to test a 100-year-old prediction of general relativity. that we should see gravitational waves. These are ripples in space-time that were predicted to occur when two black holes spiral into one another and collide. We used supercomputers to simulate these, and we saw that these waves would propagate out. And in order to test this, we built large detectors which shone lasers down kilometer-long arms, reflected them off mirrors that were super cool to within a fraction of a degree above absolute zero, and then tested to see deviations in length less than the width of a human hair. When Einstein came up with relativity, he didn't have access to any of this technology. He had no lasers, no supercooling, no computers as we would understand them. What he did have, though, was something arguably even more powerful. He had the power of his own imagination. What Einstein did was he said, imagine I am sitting on a train that's moving close to the speed of light. As this train passes by a station, it's observed by a guard who sees it get struck at front and back simultaneously by lightning. What the guard would see is a moving train and simultaneous lightning strikes. But if I, Einstein, sat on the train, I would see the station moving, and lightning would strike this train at the front before it strikes at the back. From this, he deduced that simultaneity, the order in which we see events happen, is a matter of perspective. Moving observers will disagree with one another about what happens first. Of course, no train can go that fast, not in Einstein's time, not today. He had to carry out this experiment entirely within his mind. It was a thought experiment. And thought experiments are incredibly powerful because they can go to places where physical experiments can't. I can't go inside a black hole, but in my mind I can think about what will happen there. I didn't see the Big Bang, but I can think about what might have happened at that point. The Large Hadron Collider cannot get to the energies that we need to, so we have to use the powers of our minds to imagine the kinds of evidence that we would see from this deeper theory. Okay. I want to caution you now that when you come up with a new theory, you're going to get it wrong. 99.9% of my life I spend being wrong. And I want to argue that there's nothing wrong with that. I like being wrong. The Scottish author Samuel Smiles once wrote, "We find out what will suffice by examining what will not suffice. He who has never made a mistake has never made a discovery." In the 18th century, Lavoisier had an idea that heat was an indestructible fluid. This inspired Laplace to come up with an equation that showed how temperature would flow from hot to cold regions. And in turn, Sadi Carnot used this to describe the thermodynamic engines that powered the Industrial Revolution. It would take over a century before we discover that, in fact, this caloric theory was wrong and should be replaced by a kinetic theory. And yet the wrong theory allowed us technological development, it fueled our understanding. And this is the power of being wrong. A wrong idea, if it's a good idea, could serve as a shining beacon of where to look for the right idea, where to find evidence. Being wrong can be a brilliant guide. So never fear the fact that your ideas will be wrong. To quote Ford, "I have not failed, I've merely found 10,000 ways that do not work." Finally, I want to leave you with the most important thing you can do when coming up with a new theory and when trying to test your theory, and that is to ask questions. Ask new questions. Ask questions that no one has asked before. Ask the questions that no one's thinking about asking. One example of this is the thought experiment of Heinrich Olbers, who asked a very simple question that occurs to every child. Why is it dark at night? Now, we all know the answer to this. It's because the sun isn't there. But Olbers reasoned, if the universe is infinite and full of stars, everywhere I look, my line of sight should end on a star. So the whole night sky should be as bright as the surface of the sun. Of course, we don't see this. How did we resolve this? Well, it was in fact the poet, Edgar Allan Poe, who first proposed a solution. Perhaps the universe changes over time. Perhaps the stars weren't always there. Out of this, our perspective on reality, the universe is now a living, breathing, dynamical object, not a background stage, but the stage is a player itself. This is the power of a question, because a great question might just change the whole universe. Thank you.